And so the Lagrange points are the points where the gravity basically cancels from two or more objects. Anyhow, so let's say we'll go through all the different possibilities, whether the Roche lobes are overlapping or not, or whether they're relatively close to each other. Okay, so that's going to determine the stellar evolution of these dying stars, right? So so as it says, there's depends on how close the stars are. You can have detached binaries where each has its own Roche lobe, right? That's like this picture right here. This is, well, these are actually pretty close to each other. But imagine these two stars even further apart than each other. That would definitely be detached. And then there's this semi-detached, where one star can start to transfer matter onto the other star. And usually it's the more massive star is accumulating matter, and so we'll go into that. And then there's of course two stars that are actually because when a star starts to die, it expands, right? It cools down and expands. These things can come into contact, right? So you can have detached binaries that will eventually become contact binaries, right? Just because the matter, the shells of material get larger and larger. All right, so let's take a look at this. This is an example of there's an actual star system. This is a pretty bright star. I forget where Algol is. It's let me think. I can't remember where. I think it's in the near the Big Dipper. I can't remember exactly, but it's a particularly bright star system. But this is one where the lobes are detached, right? They're separate binary systems. All right, so you have this red star that is let's see. It's two stars. Algol originally comprised a massive blue giant star into its. Okay, so this is an example of detached binaries. Two stars orbiting each other. There's no exchange of material thus far, anyway. So when and then you can have this situation where one of the stars is in the red giant phase, and it is expanded so much that the material is now within the Roche lobe of the other star. And so what happens there is that material will be drawn off, and it'll accumulate, onto the surface. And so this is sometimes, especially more. Well, we talk about this with stars as well as with planets. This is what's called an accretion disk. So you'll get a material added onto this other star. So that's called accretion. That's the idea of, slowly matter, or not necessarily slowly, but matter starts to accumulate onto the companion star, and something really interesting happens to the companion star as more and more matter falls onto it. As more and more matter falls onto it, it will actually explode. Right? These things will actually explode, and that's now this is different than a supernova. So this is considered what's called a nova, and it doesn't last. It not only does it not last very long, but it can actually repeat itself, right? Because once there's this flash due to this accumulated hydrogen on the surface. That wasn't there before on this companion star. So I'm talking about the star on the right hand side here. Once it flashes, that can repeat, and so these novas sometimes can actually repeat themselves over and over again. All right? So that's a different path towards a dying star, right? Because as it's cooling down, more and more matter enters into the Roche lobe of the other star, and that matter becomes an accretion disk, and will actually fall onto the surface of the star, and you get this giant flash of light. All right, so let's go through let's finish up this chapter. It looks like we'll be able to do that. Stars spend most of their time on the main sequence. We didn't spend a lot of time talking about that because it's rather boring, right? There's the hydrogen is turning into helium. That's it. That's what's going on when a star is in stage 7. All right. So stage 8, of course, is when the fusion stops at the core, and the hydrogen runs out, and the star's not hot enough yet to burn helium, and in fact, so a star that's maybe only about 0.25 the mass of the sun, or smaller. Remember, it can be as small as 0.08 times the mass of the sun. That's the smallest we think that stars can possibly get. You're just not going to. You're never going to fuse helium, right? It just won't. That won't happen. It won't get hot enough. All right. But if it's greater, then it will fuse helium, and when that happens, of course, that you get that well, in some cases you get that helium flash, and let's see. So then the core starts to collapse because once helium begins to fuse in the core, then, and of course, but before that, the hydrogen in the shell begins to fuse. And that's the star expanding and contracting, anyhow, what happens is the expansion becomes so great that these shells of material will actually leave the star in what's called the planetary nebula phase. Actually, before we get to that, stars like the sun, the helium burning starts with a helium flash, and then the star will enter equilibrium. That's that horizontal branch on the HR diagram. Anyhow, the star develops a non-burning carbon core surrounded by a shell of helium and hydrogen, shells of helium and hydrogen. The star expands to the planetary nebula stage. And then eventually the star begins to cool down as a white dwarf. But these things are extremely hot, and also, of course, very small because they have a very small amount of luminosity. All right. So, and the nebula this thing that's the planetary shell goes out and seeds the interstellar medium for heavier stars to be born later. All right, so high mass stars become a red supergiant, and they, the ones that are extremely massive will explode. Right, they will fuse all the way up to iron, and then when they try to fuse iron, they don't get any energy. In other words, it takes more energy than you get out for that to happen, and so the star won't continue. And at that moment, the core of those massive stars begins to collapse, and that just takes a fraction of a second, and that collapsing matter, that collapsing iron core explodes, and there's this runaway effect where the elements all the way from iron, iron and up, all the way up to uranium will fuse in just a few seconds, and so you're going to get all this matter that heavier than iron out into the universe, out into the galaxy for new stars to be born. Right? Of course, binary systems evolve differently because of the fact that there's interaction between the two companion stars, right? And in fact, you can have where matter is pouring onto one of the companions, and there's like a flash, which is sometimes called a nova, which is distinct from the supernovas when these massive stars actually explode. That's quite different. All right, and we'll look much more in detail in that in the next chapter. All right, so.